Imagine a shattered egg lying on the floor, suddenly lifting its broken pieces, dynamically pulling itself together, and leaping back onto the counter as a pristine whole egg. In the pure mathematics of classical physics, there is no rule against this. The equations governing motion and energy operate exactly the same whether you run them forward or backward. Yet in our lived reality, a broken egg stays broken. A spilled cup of coffee never regathers itself into the mug. The natural world enforces a strict prohibition on backward motion. Understanding why our world follows this strict chronological order requires us to look for the one law that the equations of motion forgot to include. The invisible constraint driving this asymmetry is a concept known as entropy. At its core, entropy measures nature's inescapable tendency to shift from order toward disorder. Looking at this summary matrix, a low entropy state is highly ordered, concentrated, and predictable, like a solid ice cube. But this naturally devolves into a high entropy state. The ice melts into an amorphous puddle as energy becomes dispersed, chaotic, and randomized. The universe prevents an isolated system from spontaneously dropping back to that highly organized, low entropy starting point, unless external work is applied to force it there. We see this principle play out in the mechanics of energy. Highly concentrated energy, like a tightly compressed spring or a boiling liquid, is highly available to perform mechanical work. But as that energy performs work and reaches equilibrium, a portion of it inescapably scatters into the surrounding environment. It diffuses from a useful form into wasted, degraded heat. Classical physicists developed a direct mathematical relationship to track this loss. This foundational equation calculates the change in entropy by dividing reversible heat transfer by absolute temperature. The math proves that achieving 100% mechanical efficiency is physically impossible. Nature extracts a physical tax in the form of dispersed, unusable energy on every action that occurs. In the late 19th century, Austrian physicist Ludwig Boltzmann brought this concept down to the atomic scale, explaining entropy through microscopic statistical mechanics. To understand his breakthrough, we have to separate a system into two views. First, there are macrostates, the observable bulk properties you can measure, like a room's total temperature, volume, or its overall messy appearance. Then there are microstates, the exact hidden instantaneous positions and configurations of every single atom making up that system. Boltzmann pointed out a massive statistical imbalance. There are very few specific atomic arrangements that result in an ordered macrostate, like a rigid crystalline structure, but there are millions of spatial combinations that result in a chaotic liquid puddle. This probability is formalized in Boltzmann's equation shown here. It calculates the entropy of a system based on the exact number of accessible microscopic arrangements that correspond to its overall macroscopic appearance. The universe does not possess a magical force that actively destroys order. It simply evolves toward a mess because, mathematically, there are overwhelmingly more ways to be disorganized than organized. This statistical certainty is codified in the Second Law of Thermodynamics. As this definition box states, the total entropy of an isolated system can never decrease over time. It can only remain constant or spontaneously increase. Because the net disorder of our universe is strictly increasing, this physical asymmetry creates the foundation for time's arrow. The chronological past will always correlate with a significantly lower state of macroscopic entropy. It is the time of defined structures and organized energy. Conversely, the future represents an irreversible progression toward an elevated state of entropy, as that energy slowly degrades and scatters. Without the continuous operation of entropy, we would have no physical mechanism to seamlessly distinguish the past from the future. If we follow time's arrow trillions of years forward, astrophysicists theorize that the universe will eventually reach a state of maximum possible entropy. In this deep future, massive cosmic structures will break down. All thermodynamic energy disperses evenly across space, settling into a dark, ambient, uniform haze. At this absolute equilibrium point, known as the heat death, no heat can flow. Stars cannot undergo nuclear fusion, and the physical processes required to support complex matter simply stop. But that is not where we are today. Right now, humanity occupies a rare, highly ordered, localized pocket of the universe. Measured against the vast timeline of the cosmos and its natural decay toward disorder, our existence in this low entropy moment is a fleeting, spectacular statistical miracle.